Section 3.2, Conditional Probability and the Multiplication Rule. Conditional probabilities are defined here as probably an event occurring given that another event has already occurred. And what this means is, what is likely this happened given that a prior event has already happened? We call this event the probability of event B given that A has occurred. For example, if we have a deck of 52 cards, which has 4 suits, hearts, spades, clubs, and diamonds, each with 13 cards, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, king, queen. So there's 52 cards total. If I pull out a king, there's now 51 cards left. And the conditional probability of pulling out a king is 4 out of 52. But what if I leave the king out and then I pull out a queen, the likelihood? There's 4 queens, but now there's only 51 cards left. So the conditional probability of pulling out a queen, given I've already pulled out a king, would be 4 out of 51, because there's still 4 queens, but there's only 51 cards left. And divide 4 to 51, I get 7.8%. Another example here, and this is more often what you'll see, is when you see a survey given various parameters. I got a survey right here, and it's looking at 2 different sets of questions. The overall question is, have you ever been offended by something in social media? One set is yes or no. The other set is the gender, male and female. And we have subsets in there where you offended with different responses based on female, yes or no, and male, yes or no. So when I look at this, if you look at the bottom right, that is the total number of people that were surveyed, 2,276. There are 1,168 female, 11,008 male, adds up to 2,276. Also, there were 1,151 yeses, 1,125 no's, and that also adds up to 2,276. So cross-tabulation-wise, these are the same total amounts, and it's subdivided by yes or no and male and female. So if I want to know the probability of being offended, given that the person is male, first, what I want to see is how many people were offended. Well, in total, it's 1,151. You go to the yes, you've been offended, straight down the very bottom, the total is 151. Now, how many males are there? It's 532. So the probability of being offended, given that the person is male, would be 532 out of 1,151. And that's 46.22%. So we can say that 46.22% of the population of individuals offended by something on social media is male. Now, independent events are events where the prior event has no effect on the next event. If I roll a die, there are 6 possibilities. If I rolled a 6 on the first time, that has no effect if I start over and then roll a different number, or say a second time. Each one's independent. Or I flip a coin, get heads or tails. If I get heads the first time, that has no effect on what I'll get the next time I flip. The probability of getting a 1 on a die when rolled is 1 out of 6, or 16.67%. Even when a coin is tossed prior, that coin being tossed has no effect on the result of what die comes up. So it's 16.67%. These are independent. Flipping a coin, even when we do it simultaneously, flipping a coin and getting a certain number on a die are independent of each other. One does not affect the outcome of the other. Now, if we have a dependent event, we already talked about this. We talked about this when we were pulling out a card. Let's suppose I had a bag of 10 marbles, 5 red marbles, 5 blue marbles. What's the likelihood of pulling out a blue marble? Well, there's 5 blue marbles out of 10 marbles total, So it'd be 50%. Now, if I do pull out a blue marble on the first pull and I leave it out, there's only 9 marbles left. So what's the likelihood of pulling a blue marble out after pull out the first blue marble and leave it out? Would be there's only 9 marbles total this time, and there's 4 blue marbles because I already pulled one out. So it'd be 4 and a 9, or 44%. The second event is dependent upon what happened with the first event. Now, the multiplication rule basically states that whatever event happens and their event comes in sequence, the outcome of both of them happening is found by multiplying them both out for each result. Now, if I pull the probability of pulling out a king out of a full deck of cards, as I said before, 52 cards, 4 kings, 4 out of 52, and that's 7.69%. Now, let's suppose, as before, I leave that king out. I've only got 51 cards. Now, what's the probability of pulling a queen out of those 51 cards? Well, there's less cards total, so that makes the denominator a little smaller, which makes our percentage a little bit bigger. Instead of 7.69% for 4 out of 52, it's 4 out of 51 now, which is 7.84%. And the likelihood of pulling out a king first, leaving king out, and likelihood of pulling out a queen after pulling out that king and leaving it out is 4 out of 52 times 4 out of 51, which is 16 out of 26.52, or 0.006. Now, what if B is not dependent on A? And this is where we talk about tossing a coin and getting heads, and rolling a die and getting a 1. As I said a few minutes ago, the one component that has no effect on the other. What's the likelihood of tossing a coin and getting heads? What's 1 out of 2? 50%. There is a head or a tail, so that is 2 possibilities. You get a head, that's 1 out of those 2, so it's 50%. My second event, rolling a 1 on a die. I can get a 1 or a 2 or 3 or 4 or 5 or a 6, all equally possible. So getting a 1 is 1 out of 6, or 16.67%. Now, if I want to know what's the likelihood of getting a head and getting a 1, and again, they're independent of each other. Whether I get a head or a tail has no effect on whether I get a 1, a 2, a 3, a 4, a 5, or 6 on a die. So, if I want to know the likelihood of both events occurring, I get 1 out of 2, or 0.5, or 50% for getting a head out of heads or tails for a coin. And then getting a 1, it's 1 out of 6, or 16.67%. When I multiply these two different and unique probabilities, 1/2 times 1/6, 1 out of 2 for coin, 1 out of 6 for a die, I get 1 out of 12, or 8.33%. That is the probability of both those events occurring. And I want you to understand, when we looked at the bell curve, and we talked about it previously, 68% fall plus or minus 1 deviation, 95%. 2 deviations, 99.7%. 3 deviations. So in other words, 95% have plus or minus 2 deviations. And a probability of 5% or less is unusual. Now, we can use the multiplication rule to find probabilities as well. And this is a real life example here. What's likely of this happening given that's happening? And we have, individuals, pre-med, who are going to go to med school. And once they finish med school, they have to serve a residency, anywhere from 3 to 5 years. Now, last year, there were 18,187 medical school graduates. And of those graduates, 17,057 were able to find a residency. What percent of those graduates were placed in a residency program? Was 1,757 out of 18,187, which is 0.9378, or 93.78%. So the probability of a residency, or a medical student getting a residency placement is 93.7%. This is independent. Now, when a medical student applies to a hospital, often and usually they're given three choices. No different in going to school. What are your three areas you want to study? What three schools do you want to go to? What are your priorities? And this study here said that of their three choices, when they get selected for residency, 79.2% of the students get one of their top three choices. So, given that the likelihood that a student who is placed residency will obtain a residency at their top three choices, and this is where we use the multiplication rule. First, they have to get a residency. They are not even in the running unless they did get that residency, which is, as we calculated a moment ago, 93.78%. And they get 79.2% chance of getting a residency of their choice, one of the top three choices. When I multiply those two numbers together, 93.78 times 79.92%, the likelihood that if a person is placed in a residency, did they get one of their top three choices, it's 74.27%. And keep in mind, this is dependent. And the reason it's dependent is because you may have three choices, and whoever deciding is independent what they want. But you cannot get a residency of choice unless you get a residency in the first place. You don't get residency in the first place, you're not getting one of those top three choices. So that second component, residency of their choice, is dependent on getting a residency in the first place. Now, this is pretty cut and dry. It's pretty simple. What's likely a medical student who was placed in a residency who did not get a residency of their choice? Well, it's simply we assume they got a residency, but didn't get their choice. It's 79.2%. I subtract 1 or 100% from 79.2%, so there's a 20.8% chance. And then the final question is, what are we going to do for a student being matched for residency and get one of their top three choices? No, we did the calculation. We figured out. Remember, unusual, as I stated 2 pages ago, is 5% or less. It's a 74.27% chance that they will get a choice. So that's not unusual.